Okay, hey guys, this is the problem. This is the video for problem 1 of tutorial 7. It says you can use either double integration or moment area. And I strongly encourage you to use moment area methods because moment area is going to be an enormous time saver. As an example, by using moment area for this first problem, you can finish it in about page and a half to 2 pages, depending on how big your handwriting is. Like for me, my handwriting is enormous. It took me 2 pages, but using moment area, you could probably finish it in actually maybe a page or page and a half. If you use differential equation method, you might finish it in a page and a half, but it's going to be a page and a half of solid equations with maybe like 60 terms total when you get to the very end. Not 60, maybe like 15 terms total at the very end. And you're not going to be happy. So I strongly encourage you to use moment area methods. Moment area is a geometric approach mostly, and geometric approaches are usually easier to do, and not only are they easier, but they're much easier to check because you can see what you're doing as you're going through the problem. The differential equation method is very hard to check your work as you're going through until you get to the point where you start plugging in boundary conditions, and if your boundary conditions don't make sense, then you pretty much have to start over. It's very hard to check your work to see where you messed up. That said, I already went over a brief introduction on moment area in the last video, so I'm going to try avoiding that here. I'm going to start off from the moment diagram. You have to derive the moment diagram yourself, but I feel like at this point in the class, you should all be able to derive the moment diagrams. If you cannot derive this moment diagram, you need to see one of us because you're going to have a very hard time for the rest of the semester. Okay, so my moment diagram. First, let me draw my shape. Actually, that might help. Let me draw this. This is drawn horribly not to scale, I guess, but that is my shape. My moment diagram looks something like this. It starts at 0, it ends at 0. It must be 0 at the hinge. It must go up, it must go back down, and it must go back up. And over here is 2pl on 9. And no, I didn't just see that. I have it drawn out before. So sorry, this is 2pl on 3. So yeah, it's not that I can do it extremely quickly. It's just that I have it finished already. So that is my moment diagram. Okay. So first things first, I guess, and the question is, where do you start? If I want to use moment area, I have to work with the section that is continuous. I have to work with an area where I have a smooth curve. And the only place where I have a smooth curve, really, is here, in this segment here. I'm going to call this H. The only point where I have a smooth segment is in this region here. If I want to, what's the best way to say this? Okay. In order to use moment area, I need to have some idea about what the deflected shape actually looks like. The deflected shape for this problem, you can kind of visualize this here, right? It has to go down here. And over here, it has to go back up. So it's going to get something like this. That is going to be, and my hinge here is going to have there's going to be a kink there. And the question is, where do I start? I don't have enough information to get the angle at A. But I do have enough information to get theta C. If I draw an imaginary tangent line at C, I can get this distance. This distance here is TBC. The distance between the tangent line drawn from C at point B with respect to the deflected shape at point B. the deflection at point B is 0. Therefore, this is going to be a right triangle. I can use that information, and this is theta c. I can use this information to help me find theta c. What is TBC? If I had drawn my things correctly here, then I should not use, let me use black. Then this should line up like this should line up like this should line up like that. TBC, like we said in the last video, TBC is equal to the M on EI diagram from A to B times x bar, which is from which is the distance from the centroid to B. Centroid to B. What is the area of this? This length here is this length here is, yes, this length here is 3L, L, 2L. Total length should be 7L. The area, this double bracket, the brackets here represent area, is equal to 1/2 3L times negative 2PL on 3. X bar is equal to 1/3 times 3L. And if I plug this all into my calculator, I'm going to get 1 divided by 2 times 3 times negative 2 divided by 3 times 3 is equal to negative 1. Where is my green marker? TBC equals negative 1 on EI. Sorry, that should not be 1. That should be P times 1, 2, 3. P times L cubed. Okay, I can use my small angle approximation. I know the height of this triangle. I know the base of this triangle. Tan theta c equals TBC on 3L. Tan theta c is approximately equal to theta c if the angles are small, and the angles will be small. Just take my word for it. And as frustrating as that may be, so this will be PL cubed on EI on 3L. The L's cancel. I get PL squared on 3EI. And let me just check my notes to make sure that this is correct. I got, yeah, that is exactly what I got in this problem. Okay, so that is that. And you're like, okay, well, I found theta c. Now, how does that help me at all? If I look at just the right-hand side of that diagram, let me draw it like this. This is my hinge. This is my roller, and this is my other roller. My deflected shape, I already said, looks something like this. My tangent line, I know this angle now. I know that angle now. Therefore, I can find this distance. This distance here is THC. Distance from the tangent line drawn at C at H to, this distance, that is THC. Yeah, and I didn't draw this correctly, but it should be like that. This is where the hinge is. This entire length here is THC. This length here is theta A times 4L. Theta A times this length I'm using my small angle approximation here, so angle is equal to opposite over adjacent. Opposite over adjacent. Angle times adjacent equals opposite. If I want to find the deflection here, that is just equal to THC minus eta A times 4L. How do I find, and again I'll go over THC again very quickly for you guys here. THC is equal to, what was my moment diagram again? What is the area of this triangle? The area of the triangle is negative, or 1/2 times negative 2PL on 3 times 4L now. 1/2 base times height. 1/2 height times base. And what is X bar? X bar, if I want to know X bar, all I really need to do is look at the distance. I'm cheating a little bit here, but if I know the coordinates of these points, I can get X bar very easily. I'm interested in X bar from this point. I'm interested in this X bar now. That X bar is equal to the distance from the first coordinate to B is 0. Right? This point is 0 units away from the hinge. Sorry, this point is 0 units away from the hinge. This point is L units away from the hinge. This unit is 4L points. This point is 4L units away from the hinge. Divided by 3. That'll be X bar. And you can do it. You can do it another way if you'd like. You can split this up into 2 triangles and find the centroid easily. But just if you don't understand where this came from, just Google centroid of a non-right triangle, and you should figure out how to do this fairly easily. 4L cubed on 3. So 4L on 3. THC is equal to, therefore THC is equal to, I'm going to skip a lot of math here. THC is equal to negative 16 on 9 PL cubed on EI. Theta A. We found theta A already. Theta A, sorry, this is theta C. What am I saying? This is, oh no, this is horrible. Theta C. Theta C. Theta C. Theta C times 4L is equal to negative PL cubed on 3EI times 4L. And I'm just trying to double check something here because I don't think my units are making sense. Oh, sorry, this is PL squared. Okay, that makes more sense now. Times 4L. If I want to find delta now, delta equals THC minus beta C4L. That is just, notice that the units here are the same. I can write that out in front. PL cubed on EI times negative 16 on 9 minus 4 on 3. And I should get negative 4 on 9 PL cubed on E.